One third attendance of the participant is of chemical engineering only here. Dr. Nitin,
Yeah, Sushant.
yeah, you asked that your student will also want to join the session. So are they joining?
I don't know. Actually, I have shared my link, shared the details to my class. Apparently, I'm teaching a course on advanced reaction engineering. So I thought that they might be interested, but let's see if they come. If they come, otherwise it's
Okay,
okay.
okay. The same link will work, and they will join automatically if they want.
Okay, okay. That is what I have done. I have shared that link to them. I don't
Okay,
know
okay,
whether
fine.
they'll join or not.
Okay, okay.
Yeah.
So, very good evening to all the participants and our eminent speaker, Dr. Nitin Padiyar. I, Dr. Sushant Upadhyay, coordinator of this Atal program, heartily welcome to Dr. Nitin Padiyar for introducing and giving his experience about the optimization in the chemical engineering. He will deliver the two topics. One is for the reactor design, and another is the optimization. So, I heartily welcome to Dr. Nitin Padiyar from IIT Gandhinagar. And now I would like to transfer the session to give a brief introduction of our eminent speaker by the Rajeshwar Kolhapure. Mr. Rajeshwar,
Yes, sir.
so please start. You can brief the introduction about our eminent speaker.
Good evening to all. First of all, I would like to extend a very warm welcome to all of you to the third session of 2-week hybrid mode Atal Faculty Development Program on Advanced Computational Intelligence Techniques for Engineering and Science Applications. This program is jointly organized by Chemical and Computer Engineering Department, MIT Jaipur. Now, let me introduce today's guest of honor, Dr. Nitin Padiyar. Dr. Nitin Padiyar is an assistant professor at IIT Gandhinagar. After graduating from chemical engineering at LT College of Engineering, he has completed his master's from IIT Kharagpur and PhD from IIT Mumbai. He has 19 years of research experience in the corporate and academic environment. Professor Padiyar's research work focuses on multi-objective optimization and model predictive control using multi-objective optimization. Dr. Padiyar has obtained Ambuja Young Scientist Award in 2004. He has also received a prestigious Indo-US Research Fellowship Award for the year 2010 for conducting advanced research at Carnegie Mellon University, Petersburg, USA for 1 year. He has 20 international journal publications and several conference publications to his name. Further, he has conducted several workshops on computational techniques using MATLAB and a national conference for industry and academics at IIT Gandhinagar. Now, I would like to request today's speaker, Dr. Nitin Padiyar, to start the session. Thank you.
Yeah, thanks for the warm introduction. Hope I am audible.
Yes, sir. Yes, sir.
Yeah, okay, good.
Yes, sir.
Okay, so I just realized that, you know, the audience is not only chemical engineer. The audience also includes people from other departments. So hopefully I'll be able to keep you motivated during the lecture, during this talk. Okay. So I'll not go too much into detail about the reaction engineering part, or rather the chemical engineering part, rather something very simple like reactor design, right? Of course, it involves a lot of details of chemical engineering, but I thought that we can understand even from a bird's eye perspective. Yeah, that is, what is design, what is reactor design, how optimization is related, what are the challenges, what are the issues, and how we can address them. So that is what I plan to do in this talk. So let me share my screen, or rather before I share my screen. Yeah. See, one thing you must understand, that whether it is mechanical engineering, electrical, or any other engineering, the moment we talk about design, we have to talk about optimization. Yeah. So what is design? In design, basically we have several options. Suppose if I talk about reactor design, that means I have multiple ways of operating the reactor. That is when actually we have to do design. Yeah. Similarly, if I want to do mechanical design, mechanical structure design, or the civil structure design, right? So then I have many options, and out of those many options, we have to select one which is the best. Yeah. So design goes hand in hand with multiple choices. Okay. Now, when we have multiple choices, certainly one choice has to be the best or better than the others. Yeah. So then choosing the best solution out of many is basically design. In simple words, of course, we can go in detail about the reactor design or any other design, but in simple words, design means making the best choice. Yeah. if I were to select a reactor, if I were to choose a reactor out of many, then I would choose that reactor which is the best out of many possible reactors. Yes. If I were to choose the right operating condition, the best operating condition, that means I have many options and I have to choose the best operating condition out of many possible conditions. That is what this design is all about. Yes or no? Yeah. Now, if I talk about design, then now we are quite comfortable that we have many choices and we have to select one of them. Now, if I were to select one of them, then there has to be a criterion. Yeah. Without criterion, I cannot select any, I cannot make a best decision, right? Yeah. So if I, let's say, want to select something, let's say if I were to go and buy a car, yeah, as simple as that. So then I must have some criterion in my mind, right? The obvious criterion that you can think of buying a car is what? Cost. Yeah. Now we know that we want minimum cost, right? So cost can be a criterion for choosing the right option. But likewise in engineering, suppose in chemical engineering, right? We want to select that process or those operating conditions which gives me minimum cost, the cost of operation or cost of fixed capital, something like that, right? So now we are quite comfortable. If you are with me, then design means multiple choices. Multiple choices means finding the best choice. Finding the best choice means we have to define the criterion, objective, yeah, based on which we can select one particular choice, right? Now, if you are with me till now, then you can also quite appreciate that many times only single criterion may not be sufficient. Yeah. So, for example, very simple example of, let's say, buying the car. Just I'll go back to the previous example, buying a car. Now, one of the important criteria is the cost. It should be as cheap as possible. Yeah, you don't want to spend 10 lakh rupees if I can get the same car in 5 lakh. Yeah, so we want it as cheap as possible. But is that the only criterion? No, right? We know for sure that there is another criterion as well. What is that? The comfort, the luxury, right or not? So often, single criterion may not be sufficient to make a choice out of many possible choices. Yeah. Now, these are the two obvious criteria for buying a car: minimum cost and maximum comfort or luxury. Yeah. So now, if I give you these two criteria, then you can probably appreciate now that you may not get a single solution if I give you two criteria, right? Suppose somebody says that I want to get the car with the minimum possible cost in the world. Then you don't have any choice. You can go for Alto, Maruti Suzuki Alto. You don't have any choice. But if you say that I want to get maximum luxury and maximum capacity, then Alto doesn't fit in that choice. You have to go for another option, right? So you can have either Alto or you can have, let's say, XUV 700 or any other Audi. Yeah. So now, if you can appreciate this example, you would say that there is no single solution for everyone. Yes or no? For someone, Alto can be the best option. For someone else, maybe Audi sedan could be the best choice. For someone else, it could be XUV 300 that could be the best. Yeah, considering what? The cost, the luxury, and the capacity. Yeah. So you cannot say that I want to pay the least minimum possible cost, that is, let's say 3 lakh rupees, for example, but I want to get 7-seater and I want to get the ultra luxury comfort. You know, you can't get all these three solutions in single car. Can you do that? No, you can't do that, right? So that is why we have multiple options. If I have to spend the minimum cost, then I have to compromise into luxury, and the option is this. If I can spend as much money as possible, I can go for ultra luxurious car, Rolls Royce, right? And but then it will cost a lot, right? So depending on to our preferences, depending on to our priorities, we can select one out of many possible options. Yeah, that means I have many solutions, and depending on to my preferences, I can select one of them. Yeah, when this happens, when I have multiple criteria. If I have single criteria, that minimum cost, then that's it, ultra final, done. Yeah, but now if I say that, well, I can afford to spend a little more than that. Let's say 7 lakh rupees, 10 lakh rupees. Then I have many options, right? So the point is that if you have a single criterion, that's it, single solution you get. If you have multiple criteria, then you have many options, you have many solutions, and then based on my priority, I can select one of them. Yeah, but getting that menu, that if I want this much luxury, if I am ready to spend this much money, then what is the best option available? I have this solution. Yeah, and if I'm ready to compromise into either cost or luxury, get me the other solution, which is the best. Yeah. So in other words, I'm saying that, you know, if I get a menu, how we go to the restaurant and we ask for a menu that, you know, I want to buy this, then I have many options and I can select one of them, right? So likewise, if I get a menu that for this much luxury, you have to spend this much money, and this is the option. For another extent of luxury, the corresponding amount of money is this much, and this is the model, this is the car. Yeah. So if I get that solution, isn't it so useful for running the reactor, for operating the reactor, for operating any particular system? Make sense? Yeah. So this is a very simple example that you can relate with multi-criterion optimization based design. Yeah. Now so how there are two such criteria for selecting a car, for buying a car. So likewise in engineering as well. So in engineering as well. For example, in chemical engineering, if I were to design the reactor, what is the job of the reactor? It converts the reactant into a useful product. Yes, that is what is the reactor's job. Now, selecting the so designing this reactor may involve more than one criteria, right? Since there are many people who are other than chemical engineers, I would say that I'll specifically give some examples, right? If I were to run a reactor, you know, I can think of course, you know, I want to run the reactor so that I can make the maximum money and minimum cost. That is the gross, or rather, that is the you know, abstract objective. No one wants to run a reactor or industry which makes loss. Yeah? So ultimately, we want to make money. Yes or no? So that is the base criteria, that I want to make money and minimum cost, right? But we cannot simply design a reactor based on this. Yeah, we have to relate this criteria with something measurable criteria. So that is what we are going to take a look at it in today's talk. Yeah. So with a particular example, I'll showcase how it works. And feel free to stop me anywhere in between, and I'll be happy to answer. Okay. So I think now you'll be able to see my screen, hopefully.
Yes, sir.
Yeah, very good. So what I'll do, just a minute. Yes. Okay. So what I thought that uh, a couple of years back, one of my MTech students, he had done this work on multi-objective process optimization of a reactor, okay, which produces hydrogen from natural gas. Yeah? So now you must be aware that hydrogen is one of the important energy sources, and now the buzz is that the cars or vehicles also soon run based on hydrogen fuel, yeah? Because of many interesting reasons. Okay? So basically, hydrogen is in demand. Now, if you ask one more question, that where do we get this hydrogen from? Yeah. So industrially, or most of the hydrogen that we get in the market, typically it gets produced from natural gas. What is natural gas? Primarily methane gas. Yeah. And naturally, and the natural gas is available naturally. So we get the natural gas from um, the earth or from the sea, and we process that and we get the hydrogen. Yeah. And hydrogen is a very good fuel. So there is a demand for that. So what we thought that let us design the reactor which produces hydrogen. Yeah. So based on multi-objective process optimization. Okay. What is that? What are the criteria? How do we do that? That is what we are going to talk about. Yeah. So I give this credit to Zafar, who worked for this, and he did very nice job. And that is what I'm going to show you. Okay. So I'll not go too much into detail because many people are there who are not from chemical engineering. So I'll not go into reaction details part. Rather, I'll focus on to optimization part. So typically, generally in industry, this hydrogen that is manufactured, that is synthesized, is in a tubular reactor. And in this tubular reactor, there are catalyst particles, solid catalyst particles. Yeah. So the natural gas along with some other gas, yeah, some recycled gas, something else. So that those two are sent into the reactor at the inlet. Okay. And at the exit, what we get is a product. Yeah. And hopefully this product should contain more of hydrogen than anything else. It cannot, any reactor cannot convert entire reactant into total product. There is always unreacted reactant and side products. We have to deal with that, right? Okay. So uh, conventionally, this reactor is tubular reactor. So what we uh, came up is that what if I use a spherical reactor? Is there any advantage with spherical reactor? In fact, there are many, but we quantify that and we actually design the reactor uh, uh, very nicely using optimization of these two reactors. Okay, and I'll tell you more details about that. Very interesting details. Yeah. So in tubular reactor, what happens that my feed goes from left and goes out from the right. In spherical reactor, I introduce the field. I introduce the feed from the surface, outer surface, and the product is taken out from the center. Okay, so there is a pipe in the center which I can take it out after the reactants pass through the reactor, reaction occurs, and we get hydrogen, and we take it out from the center of the reactor. Yeah, this is the overall picture. Now, so far in the industry, 99% of the times, I think in 100%, all the reactors are tubular reactors. But there is nice advantage if I use spherical reactor. Okay, what is that? We'll see that. Yeah. So there are primarily three advantages. Yeah. See, in tubular reactor, no, what happens that when I pass the gas feed, because of the catalyst packing, uh, the pressure at which I send the gas, by the time it comes out along with the product, my pressure drops because of the friction, because of the reaction stoichiometry and so on, right? So imagine that I'm pumping the gas at a very high pressure, but by the time it comes out, it loses its pressure. Okay. Now some of the reactions occur only at very high pressure. So if my inlet pressure is not sufficiently high, then I'm not going to make some nice products. Yeah. So I have to ensure that my inlet pressure is very high, sufficiently high. Yeah. Now, if I lose too much pressure in the reactor, then I really have to pressurize the feed gas a lot. Now, if I pressurize a lot, that means I have to use compressor to a greater extent. Now, running a compressor is a very energy intensive process, energy intensive option. Yeah, so I have to lose a lot of money in just compressing the gas. It is very, very costly affair. Yeah. So then we thought that can we use these as the criterion? What is the criterion? That the power that we lose, the electricity power that we lose because of the pressure drop. Nobody till 2021 before us, nobody had done this. So we explicitly thought that can we use power consumption as one of the criteria for designing the reactor? Well, nobody had done that. So then that pressure loss or the power consumption is quite less in spherical reactor as compared to tubular reactor. Yeah. So there is one reason. Okay. And because of that, implicitly, we also get large production capacity. That is more detail of chemical engineering, and I'll leave it for now. And uh, basically, the amount of catalyst that I need to process, that is also quite less in spherical reactor. Yeah? So these are the few of the advantages. So we thought that let us do a comparative study. But before that, we also realized that nobody in cylindrical reactor, like tubular reactor, nobody had done design based on multi-objective optimization. So, we found two problems and we solved both of them. And I'll show you the results very soon. Okay. Yeah. So this graph, if you can appreciate, for spherical reactor, which is blue in color, the pressure goes from 3 to maybe 2.97. So pressure loses very less. Pressure drop is quite less, which is a good news. On the other hand, in tubular reactor, the pressure goes from 3 to 2.35. So there is large pressure drop. That means it will demand more power consumption. Yeah? This is a typical result. Feel free to interrupt me, yeah? Ask me any question. Okay, so this is some literature review. I'll not go too much into it. Uh, uh, Optimization, by now, probably you might be aware that mathematically, if I just symbolically, if I write, what is math? How do we, write down the, just a minute, I'm trying to see if I can use my pen here. Okay, good. Yeah. Yes. Yeah. So optimization. So if you are with me so far, if I you know put down the optimization activity, the design activity symbolically, mathematically, yeah, this is how we can do that. That either we want to minimize some cost or some undesired aspect, or we want to increase the profit or some desired quality. So that is why I would like to minimize f of x, where x is a vector. When I say x is a vector, which means that I can have multiple variables. See, I cannot minimize something. I cannot minimize cost by doing nothing. I have to do something. Doing something is the variable x. There is a control action or other, decision variable that I have to make choice. Yeah. So f is the objective function that I would like to either maximize or minimize. Here I mentioned minimize. And in general, f also could be a vector. That means I can have multiple criteria. One could be maximization, one could be minimization, so on. So symbolically, I want to minimize uh, f vector. That means I want to minimize f1, f2, f3 up to fn. And for that, I will take an action in terms of x. So symbolically, we do it like this. But in doing so, I have to follow several constraints. I cannot practically I cannot do it get away without any constraint, right? Um, yeah. So the constraints could be of equality type. Yeah, that is h of x equals 0. Yeah. So that could be one. And inequality constraints could be gx less than or equal to 0. Yeah. So those who are from chemical engineering, they can appreciate that mass balance, energy balance are equality constraints. Gx less than or equal to 0, like temperature should be less than or equal to 100 degrees centigrade, 200 degrees centigrade. That's an inequality constraint. Yeah? And I can have direct constraint, bound constraints onto my lower bound and upper bound, onto my variable in terms of lower and upper bound. Yeah. So, uh, so uh, uh, this way of defining a problem is the optimization. This is how we can define the optimization problem. Yeah, where I want to minimize something. It could be more than one criterion with respect to variables x, and I could have inequality constraint, I could have equality constraint, and I could have bound constraints as well. Okay. Now it is not going. Okay, so we are quite comfortable in optimization. We have seen earlier in UG as well that if I want to minimize f of x, then we know that where the slope of f of x versus x is 0, that is when we get the minimum function. But if I have, let's say, multiple criteria, let's say 2 criteria, f1 and f2, then as I mentioned, we don't have single choice. We have many choices, many solutions. Yeah, nano versus OD. Yeah. So in single objective, we get only one solution. In multi-objective, we get many solutions, and we have to we have to select one of them based on our preferences. I hope you are with me. Feel free to ask me anywhere in between, interrupt me. I'll not go into literature review. Yeah, but let me summarize the literature review that my student did. He said that, if I want to manufacture, if I want to produce hydrogen from natural gas, then all the literature that is available in the open literature, you know, based on optimization, the criteria that were used to do optimization based reactor design for hydrogen production, there are primarily 4 criteria people had used. Not all of them all of them in a single paper, but somebody had used maximization of hydrogen production, somebody had used maximization of methane conversion, somebody had used minimization of the carbon dioxide emission, and somebody had used uh, to synthesize a synthesis gas rather than hydrogen. That is a proper ratio of hydrogen and carbon monoxide. Okay, so no other criterion was used for the reactor design for hydrogen production from synthesis from that natural gas. Nobody. The entire literature till 2020, nobody had used any other criterion than this. And in doing so, as I mentioned earlier, that you cannot do optimization, you cannot design without taking any action. So action variables in the literature, entire literature that was available was 3. Only 3, design variables were used. There is temperature, oxygen to methane ratio in the feed and steam to methane ratio in the steam. So these were the three variables people had used, and objectives were the above four. Yeah. So then, based on brainstorming sessions, we realized that nobody had used power loss as an objective function for designing the reactor in the literature till 2020, before we did. Okay. So, and power loss is a very, very important uh, criterion. Why? Because it directly affects the economy. Yeah. Then there was no literature on multi-objective optimization based spherical reactor design. Nobody had that, and uh, there was no literature on multi-objective optimization based tubular reactor design as well, with power loss as an objective. Yeah. So we saw that this is the gray area. This is the area which is not at all explored by any. Yeah. So these my student could do after 5 to 6 months of his efforts. So what we did, that we will target this. Yeah, this summary, that is the outcome. So first, what we did, that nobody had done multi-objective automation based design for a tubular backbed reactor. Tubular reactor was used, but nobody had done multi-objective design for tubular reactor with power loss as one of the objectives. So that is what we first did. Okay, so now what we did, our job became simple after this survey, and we said that, okay, tell us, if I have natural gas in my feed, then tell me what are the reactions occurring. Now, these are the reactions occurring. So here is not our contribution. We said that people have already done. Chemists had developed this chemistry earlier. We don't have to reinvent the chemistry. So we took it. People had written the model equations for the tubular reactor for synthesizing hydrogen from methane gas, natural gas. Yeah, that also people have done it. So we don't have to do it again as research. We took that. We started from there. Okay. So what are those equations? The mass balance. What is the mass balance? Something goes in, something goes out, something reacts in between, and that's it. How do we write it properly? Is in terms of mass balance. This is this equation, left hand side. Okay. Then this is about the material concentration or composition. Why is the composition? Don't go too much into detail, but something goes in, some material goes in, out, reactor. That is what, and the equation is this. Then not only material, some energy, some heat. Heat goes in, heat goes out, something produces in between, or something gets consumed. So effectively, my temperature is not constant throughout the reactor. How does it change? Like mass balance, we have energy balance. Yeah. So how do we do that? There are nice, those who are chemical engineers, they know how to do that. We learned that in third year chemical engineering course, reaction engineering. Very simple. Then that is not it. How pressure changes. You cannot get this answer using mass and energy balance. Rather, if I want to know how the pressure also changes along the length of the reactor because of the friction, because of the pressure loss, the equation for that is this, the third equation, Ergun equation. How the pressure changes along the z direction, axial direction. Yeah. So all these three equations, if you look at it, left hand side, how the composition changes, how the temperature changes, and how the pressure changes along the length of the reactor. That information we get it from fundamentals that we learn in third year and fourth year chemical engineering. Okay. Even though you're not a chemical engineer, you may probably appreciate that, yes, something we can write mathematically. Yeah. And this is not rocket science. This is very simple. We learn it in third and fourth year chemical engineering. Okay. And how the reaction progresses, what is the rate of reaction, what is the speed of reaction, that information also is available in the literature. And we did not research on that. We looked at, we assumed, we took it from the literature, and we give the credit for that to them. Yeah. And these are the guys who have done this. Yeah. So based on this, we solved these equations and we simulated the tubular reactor for hydrogen synthesis. and we matched our results with the published results, and we developed the confidence that yes, what equations we have solved, they are right because they match with the standard solution available in the literature. So that developed the confidence that yes, now we are fine. This is not our contribution. This is not our research. But starting from this, we solved optimization. Okay. Now, move multi-objective optimization. Yeah. So as I mentioned earlier, that tubular reactor, nobody had used multi-objective optimization. Okay. So we did it. We said that, okay, I want to maximize F1, which is hydrogen production, and I want to minimize carbon dioxide, and both of them simultaneously. Now tell me, what are the possible solutions? Yeah. So with a car example, now you are aware that if you have single criterion, then you get single solution. But if you have multiple criteria, then you don't get a single solution. You get many solutions. Yeah. So it makes sense that here also we get many solutions. Just give me a minute. Okay. So now the methodology is, I'm not this, let me see if I have, yeah. So first of all, yeah, so these are the two objectives. The variables are X. I'll tell you what are those X. The constraints are the material balance, energy balance, and momentum balance equations. And the variables are steam to methane ratio, oxygen to methane ratio, and feed temperature. These are the variables, and the constraints, the bound constraints are there on temperature, steam feed, and oxygen feed. Yeah, so they are the basically um, constraints. Now, believe me, this is just one slide, but I tell you, this is the entire summary of the literature review and defining the problem. Yeah. So this is the crux after the brainstorming session of 6 months. Okay. So what it may look very simple, it has come out after a lot of hard work of one of my students. Okay. Because once you define this problem, which nobody had defined solved it earlier, that is contribution. So how do we solve it? You might have, I'm not going into detail about how we solve it because there are many solvers which can solve this problem. Yeah, I'll just mention one of them, like non-dominated sorting gene algorithm, NSG, yeah? Multi-objective differential evolution, another weighted sum approach, yet another approach of solving the multi-objective problem. Which problem? This this multi-objective problem, maximizing hydrogen production, minimizing carbon dioxide emission, subject to these constraints. This problem can be solved mathematically, can be solved numerically by NSGA2. Okay? One of the many solvers. And that too, there is a nice solver available in MATLAB. So you don't have to write down the code of crossover and mutation and so many other steps of genetic algorithm. Rather, you can use multi-OBJ-GA subroutine in MATLAB. Huh? That is what we had done. So as I mentioned earlier, what is the time right now? Yeah, we have some time. I guess 7:50 we have to end, no, Sushant?
Yeah, now we can take a
Yes,
break.
sir.
It is about 250 minutes, so we can take a 10-minute break and then we can start the same topic or another topic.
Yeah, I think we'll begin from here. We'll start from here, and then if there is time, we can go to the other topic as well.
Okay, fine, doctor.
So is this the right time to take a break?
We can take a break
Okay. So we'll meet after 10 minutes or
after 10 minutes. So Rajesh sir, please you can inform to all the participants accordingly.
Let's take a break for 10 minutes.
Okay. Yeah. I'll also come back after 10 minutes. Huh? Yeah, so let me know once you want me to start.
Yes, sir. You can start.
Yeah, Dr. Nitin, we can start.
Okay, yeah. So as I mentioned earlier, this is an application of designing a reactor and tubular reactor for producing hydrogen from methane gas or natural gas, right? And we realized that single criterion may not be sufficient for the reactor design. And and from literature we realized that certainly there are three objectives or criteria that we can use. Yeah, one is hydrogen maximization, and one is carbon dioxide minimization. Yeah. So this hydrogen I want to maximize. Yeah. And carbon dioxide I want to minimize. Yeah. So the ideal point for me is this. Yeah. That so this point corresponds to maximum hydrogen and minimum carbon dioxide, but this is not realizable. You cannot get that. Whatever temperature, whatever the feed temperature, feed concentration of carbon dioxide and methane and water, you don't get that. Okay. So if I can get either maximum hydrogen, that is point A, or minimum carbon dioxide, which is this point, but then you have to make a deal. You have to make a compromise that if I want maximum hydrogen, then the corresponding, I can get that. This is the maximum hydrogen possible. But then correspondingly, I also have to compromise in terms of large carbon dioxide emission. Yes, I have to deal with that. Similarly, if I want to minimize carbon dioxide, which is this point B, then the corresponding hydrogen production is also quite less. Yeah, so this we have to deal. But before we solve this problem, before we solve this problem, uh, getting the solution was not so obvious. Yeah. So if I, let's say, begin solving this optimization problem, I'm just trying to search a pen. Hopefully this one. Yeah. So I may get some points here, some points here, some points here, here, and so many other locations. Yeah. And after solving this optimization problem, we get this solution. Okay. So this solution you have obtained after sufficient number of effort. Okay. And ideal point cannot be realized, but this is the maximum possible good results that we can get. And this is that solution. And this is a set of solution. By the way, so point A, if I take, then the corresponding feed conditions are these, that temperature should be this much, oxygen should be this much, and water should be this much in the feed. Yeah, and the corresponding hydrogen or carbon dioxide that you get are this much. So these are the objectives. These two are objectives, and these are the action variables. These three are the action variables. And each of these points on this curve, correspond to a set of action variables. Yeah, so 5 such points, A, B, C, D, E points I have tabulated here and shown over here. Yeah, and if I let's say use my feed temperature of 2000 Kelvin, oxygen to methane ratio as 0.34, and water to methane ratio is as 4, then I'll get maximum hydrogen, and the corresponding carbon dioxide this much. Yeah, and depending on to my choice, I can choose any of these solutions. Yeah, so this is like a menu. Yeah, so this is a menu given to the designer. Okay, that you choose your preference. You want to go for maximum hydrogen, minimum carbon dioxide emission, or anywhere in between. You can go even for point C, where you get sufficient number of hydrogen and sufficient and good amount of CO2 reduction as well, like this point. Yeah. Yeah. So this is a menu given. Now I tell you, this menu is very, very important, because based on this, we can make a choice, and we can run the reactor. So it's a great information, I tell you. Yeah. Of course, I haven't shown you how to solve this problem, but if you're interested, you can explore multi-obj GA in MATLAB and you can solve such a problem. Of course, it, it will require a lot of troubleshooting and so on, but you can do that in principle. Okay. Now, for these 3 points, A, B, and C, for these 3 points, that is A, B, C, and A, these points, if I run the reactor, that is, if there is a tubular reactor, then and the corresponding these feed conditions I provide into the reactor, then the corresponding temperature, how does it change? It changes like this. Yeah. So, for example, point A, which corresponds to maximum hydrogen, the temperature changes like this. That means I'm operating at a very high temperature, because at high temperature I get good reaction and good desired reaction, and then I get a lot of hydrogen production. And the pressure changes in this fashion. So pressure drops also quite a lot, the red color. Okay, so that is where I have to deal with that. And such are the profiles for the other 2 points as well. Okay, so as I mentioned, I'm not giving too much detail about how to solve this problem, but then we realized from the literature that nobody had, as I mentioned, nobody had used power loss as the criterion for designing the reactor. So we did another multi-objective problem based reactor design, and this time, instead of carbon dioxide minimization, we said that we will minimize the power loss. Yeah, or you can also imagine power consumption for running the reactor. Yeah, more power consumption means more loss, more cost. Yeah, and I want to maximize the hydrogen production for the obvious reason, right? And again, we got this multiple solutions. Yeah, so ideally, I want minimum power consumption and maximum hydrogen production. So that is why this point turns out to be the ideal point, but this is not realizable. Yeah, because I have mass balance constraints, energy balance constraints. Those constraints have to be met. And so the practically out of many possible solutions, the closest curve that you find from the ideal point is this curve. Yeah. And each point on this curve can be obtained by correspondingly choosing the feed conditions, that is temperature, temperature and steam and oxygen. Yeah. So and these are the typical pressure profiles and temperature profiles inside the reactor for the 3 points. Now I'm not doing analysis of these variables, because many of you will not be able to understand those, especially those who are from other than chemical engineering discipline. Okay. And the third problem, we took the third combination, like power loss minimization and carbon dioxide emission minimization. Yeah, both this minimization. So I want to minimize power loss and I want to minimize carbon dioxide. So this is the ideal point. Yeah. So all the points which are closest to this ideal points, those are these points. Yeah. And again, I have several points on this curve which can be realized by appropriate by correspondingly feeding the right conditions. Yeah. And these 5 points, A, B, C, D, E points are tabulated here as well. Okay. And the corresponding temperature and pressure profiles. Of course, there are other profiles as well, like carbon dioxide profile inside the reactor, then hydrogen concentration profile inside the reactor, but that I'm not plotting because of obvious reasons. And finally, the problem that is very important, that and first time we did, like all the 3 objectives, I want to maximize hydrogen, I want to minimize carbon dioxide, and I want to minimize power loss. Now, simultaneously, if I do this for all the 3 functions, the results are summarized in this 3D graph. Okay, and each of these points is the designed reactor problem, design of the reactor, right? And depending on to my preference, that how much power loss I want to manage, how much hydrogen I want to manage, I want to produce, and how much carbon dioxide emission I can afford. Accordingly, I can choose any of these points. Yeah. So getting this menu, considering all the 3 functions, all the 3 criteria, is, I tell you, very, very important, very important. So if I give you these solutions to a design engineer or even the operator, will be extremely happy that, oh, this is what I want, because now I know that if I want maximum hydrogen, that how much corresponding carbon dioxide emission I'll get and how much power loss I have to afford, right? And vice versa. Yeah. And interestingly, 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 uh, if I make this projection of 3D graph onto 2D on, let's say, carbon dioxide and hydrogen, the solution that we had obtained in the previous problems, no, hydrogen and carbon dioxide double objective problem, those are this purple line. So those solutions are also obtained by projecting this 3D graph onto 2D graph. Yeah. If you have a question, you can ask me on this. I'll be very happy. And likewise, hydrogen and power loss. Yeah. Effectively, what I'm saying is that if you solve this 3D problem, no, three-dimensional multi-objective problem, you have solved two objective problem for each of the three combinations. Yeah. So this is the superstructure of all the three problems that we have that we can solve in single shot. Yeah. So this work we had published in International Journal of Hydrogen Energy, very reputed journal, in 2020, and most of the credit goes to my student Zafar Ahmed. Yeah. And so far, is there any question? No? Okay. So, this is then, so as I mentioned earlier, that, this, no, this hydrogen production was conventionally done in a tubular reactor. Yeah. But there are evidence that if we use spherical reactor, we get even better production. Okay. And we get very less power loss. So then we actually said that why don't we actually explicitly solve this design problem using multi-objective problem? Okay, and that is what we did. What about spherical reactor? So we did that. So again, you can write down fundamental equations that we learn in our four-year undergraduate program, right? If you sit down quietly, nicely, go through that, you'll be able to understand this quite nicely. I'm not going to discuss that, but people have developed this. Yeah. And this time, what we did, we solved the same three problems. Multi-objective problem one, which is hydrogen minimization, hydrogen maximization and power loss minimization, and same constraints. Only the equations will be different. The material balance equation will be slightly different for spherical reactor. Energy and momentum balance equations will be slightly different for spherical reactor. But the approach will be the same. And what we did, we actually did comparison of spherical reactor and the tubular reactor. Now, mind you, that this tubular reactor is conventionally used 99% of the time in the industry. Nobody uses spherical reactor. And there is a strong reason why we can use it industrially as well. Okay, and that is what we demonstrated here. And we said that, well, if you want to maximize hydrogen, tubular reactor gives you this much hydrogen, so does this spherical reactor as well. But imagine that the corresponding power loss that you get is using this green line, no, the green curve. The corresponding power loss is this much, like 13 into 10 to the power 7 watts. Imagine so many energy units. And by the way, 1 kilowatt hour is 1 unit, right? Which costs about approximately 8 rupees. So you can convert this into units and you can do some rough calculation. On the other hand, if you use spherical reactor, imagine for the same hydrogen production, you get to spend only 4 into 10 to the power 7 watts. Imagine like 200 times, or rather, sorry, 20 times. This is 4 and this is 16, 14, no, 3 times, approximately 200%. I am able to save energy by threefold, approximately 2 to 3 fold. Yeah. So imagine that if you are spending, like, let's say, 10 lakh rupees every day for energy consumption with the tubular reactor, you'll be able to do it only with 3 lakh rupees per day. So directly 7 lakh rupees you'll be able to save just with these solutions, or at least with this approach. Okay. So we did this one-on-one comparison using multi-objective techniques. Okay. So this both these curves are obtained by solving multi-objective problems, one for spherical and one for tubular reactor. Yeah? And very similar analysis we have done how we had done it for tubular reactor. Okay. I'll not repeat this again. Yeah. And these are the temperature pressure profiles inside the reactor. And second problem, power loss and carbon dioxide. Again, we compared that of the again we compared the spherical reactor results with the tubular reactor. Yeah, this is the summary. Look at this. This is the ideal point. I want to minimize power loss. I want to minimize carbon dioxide. This is the ideal point. And look at this. This black color curve is closer to the ideal point as compared to this green curve. Now, green curve is tubular reactor and black curve is the spherical reactor. So explicitly, I can say that how much benefit I'm getting with the spherical reactor as compared to the tubular reactor. You know, I can quantify that, and that is what we have shown in this paper. Okay? And these are the results, tabulated results. Okay? Very similarly, the third objective, that is carbon dioxide minimization and hydrogen production maximization. We don't get too much benefit here, but we have got extremely large benefit in the other two multi-objective problems. Yeah, here is the ideal point, and tubular reactor is slightly doing a better job compared to spherical reactor over here. But as compared to power loss, there is no comparison, I tell you. Look at this. This is the ideal point. This is the ideal point, and black color curve is so much close as compared to the green color curve. So much close. You see that? Okay. And finally, three objectives. Yeah. All the three objectives simultaneously. This is the ideal point. And look at these black points. They are very, very close to the ideal point. And the green points, they are far away. Okay. So explicitly, we quantified the benefits of using spherical reactor as compared to tubular reactor for designing design and operation. Yeah. And this study was very much appreciated, and we published that into another article in the same journal, International Journal of Hydrogen Energy. Okay. Again, the work was completed by my MTech student, Zafar Ahmed, and most of the credit goes to him. Okay, these are the projections and so on. I don't want to repeat that. Okay, so this is the first topic of my talk. Depending on the time, I'll take the second topic. So I'm not in hurry to cover and second topic. But I'll be very happy to answer any question if you have.
Dr. Nitin.
Yeah.
You have used the FMinCon in the MATLAB for this multi-objective optimization for the power loss maximization and S2 exit maximization.
Oh, very good question. So FMinCon in MATLAB, no, it solves single objective problem only. Yeah. So
Okay.
for double objectives and three objectives, FMinCon doesn't work. So we used GA multi-OBJ subroutine in MATLAB instead of FMinCon.
Okay, fine.
Yeah. But you're right, for single objective problem, you can use FMinCon. Yes.
Okay, thank you.
Is there any other question by anyone else? Okay. So here, in summary, I would say that with optimization and especially multi-objective optimization approach, we can design the reactor and we can actually get the benefit by solving this problem, and we can quantify and we can make we can make a choice based on the criteria that we define. Okay, and we get a menu of all the solutions, and depending on the priority, I can choose any one. For example, analogously, it's very similar to choosing a car based on just the cost or just the comfort, or the combination of the two. So accordingly, you can choose the option for buying a car, and very similarly, you can choose the operating condition based on the three criteria: how much compromise you have to make into criteria, which criteria is more important. Based on that, I can choose uh, one out of many possible solutions. Okay. Okay. So if you have no other question, maybe I can start with another topic.
Yeah, please go ahead for second topic.
Yeah. Sure. So this is a dynamic optimization problem. Okay. So this work was done by my PhD student Narendra, and this work was published in 2017 in Chemical Engineering Research and Design. So let me just give an overview of this problem. Okay. Okay. So so if you go back and look at the previous problem, no, so there it was a steady state problem. Okay. So those I know that many of you are not from chemical engineering, but especially I'll tell a little bit to the chemical engineers now that tubular reactor can be operated at steady state conditions. And most of the time in industry, actually we operate the tubular reactor at a steady state condition. Okay, and that is why the design of the reactor is also done at steady state conditions. Yeah, so that is why um, uh, um, it is slightly simpler to solve. But imagine that suppose I have a reactor, a batch reactor, okay, a semi-batch reactor, wherein there is something in between, something is there within the reactor A, and other thing I'm inserting. So it is like A plus B going to C, and C is my product. I want to make product B, C. Yeah. So if I'm supposed to add B inside the reactor, the question comes that how should I add B? Should I directly add B at the beginning, or should I slowly add beginning? Should I add B slowly, or should I add fast in the beginning and slow in the end, or the otherwise? Or you have infinite possibility that how you can add B into the reactor. And mind you that however way you add B into the reactor, accordingly you will get the product. Yeah. So if you want to get the maximum product, there is only one choice. Yeah, how we can add B in the reactor so that you can get the maximum C. Yeah, this simple example that which makes the basis of designing the reactor. Yeah. So we looked at the design problem in this fashion, okay, and we applied that to a chemical reactor. Okay, I will not go into this. I'll come to it a little later. But I want to show this that there is a all these biological products, no, all these biological products. Maybe I'll come to it a little later. If you can recall one of the simple biological reaction, no, it is like milk converting into curd. The process of making curd from milk is a bioprocess, right? And you can also imagine that, it's a slow process. Overnight, it's a business of overnight. So you keep milk with some curd overnight, and in the morning you get the curd. So it takes 7-8 hours to make the curd. So all these and this is the typical nature of the biological reactions. Yeah. So all the biological reactions that occur, generally they are very slow, very, very slow. Yeah. So if it is slow, yeah, and mind you that all those pharmaceutical reactions, or rather all these pharmaceutical products, yeah, that is antibiotics and aspirin and so on, those are also obtained from biological reactions. So those are also very slow. Now, the problem with these slow reactions is that, I have to wait a lot. That means if I want to make large production, then it is not very easy, right? Why? Because the reaction is very slow. I have to wait a lot, or I have to use too many reactors or too large reactor to compensate the time with large production. Yeah. So, so this is one of the typical nature of a biological process. Okay. So these bioreactions are typically done in a batch reactor. Now, what is batch reactor? The same example. We take a bowl of milk, we add some curd, and we keep it overnight, and that's it. This is a batch process. Yeah, we start with something, we leave it, and then we get the product after some time. This is a batch process. Okay, and industrial fermenters or industrial bioreactors are typically run in a semi-batch mode. That I'm starting with something A and I'm adding B continuously with time. But how do we add is the million-dollar question. Yeah. So that is what we addressed in this question, in this problem. Okay, and that is what we solved it, and my student worked on it. So if if I take one representative, very simple biological bioreactor, if I take, then it has two products, PM, PT, some two different forms of the protein, okay, some biomass, the live cells, the substrate, the reactant, and the volume of the reactor. So those five variables, they change with respect to time in the reactor. Okay, and these are the detailed equations. Okay, which can be in a compact manner can be written in this order differential dx by dt equals some function of t, x, and f, where f is what? Something that I can change. What can I change? The flow rate that I add in the reactor. That is something that I can change, because that is more interesting to me. With that, I can do optimization. Remember that if I want to maximize something, minimize something, we have to take some action. That action is this f, the flow rate of B that I add in the reactor. Okay. The question is how? Let's look at that. Yeah. So here, so the variables have defined. Okay. And there are some other auxiliary equations. I'm not going there. Okay. So after a lot of, after again literature review, we realized that we can maximize the product P. Yeah. And productivity, and if I divide by TF, see TF is a batch operation time. Now remember that I want to get maximum product in minimum time. So if I can maximize P upon TF, that is what actually I want. Yeah. So large production in minimum time is what I want. Yeah. So this is the one criterion I can choose to design the reactor, to design the fed batch reactor, design the semi batch reactor. Yeah. That I call as JP. Yeah. By carefully adding the flow rate of B in the reactor. Okay. Now, mind you that this F, the flow rate of B that I add to the reactor, many options. Slowly, fast, first fast and then slow, first slow and then fast, and so on. So many options. Yeah. So that is why we need to solve an optimization problem. Otherwise, you don't need. Okay. And the constraints, all those equations, differential equations that I've shown earlier. Now, mind you that those, at least from chemical engineers, they'll understand that semi-batch reactor is a unsteady state reactor. Yeah, always you run in non-steady state condition. You don't get a steady state because every time you are adding something. So that is why this the equations are also correspondingly written, with differential equations with independent variable time, just an additional information. Huh? Yeah, and the constraint is that my flow rate cannot exceed 2.5 because of the pump limitation, and it cannot be less than 0 for obvious reason that I cannot add negative flow rate. Yeah, and so this is how I can define the optimization problem. Yeah, now mind you that even if I solve this single objective problem, yeah, there are constraints which are dynamic in nature. Yeah, So I'm maximizing something with respect to some variable and these constraints, which are dynamic in nature. And that is why this is called dynamic optimization. Yeah, or people call it optimal control problem as well. Okay, so this is the origin of dynamic optimization, and I tell you, it is not very easy to solve this problem. Yeah, but at least let us understand the application of this problem. We realize that this is not the only criterion which is important for designing the reactor. We say that, you know, maximizing product is one thing, but minimizing the amount of the substrate, the reactant, is also important. Why? Because many times the reactant is very, very costly. The substrate is very costly. Yeah. So that is when this concept of yield comes into picture, that I want to maximize the production, but minimize the amount of the feed that I give. Yeah. So this is another criterion, and the same constraints. Okay. And what we said that these are the two objectives. And the third one, we realized that after doing a lot of review, we realized that we can use the third objective, third criterion, is the time itself. For how much time I want to run the reactor. If I can do that in minimum time, it is great. Yeah. So this I want to minimize, this I want to maximize, and this I want to maximize. So can I do that simultaneously? And this time, as compared to the previous spherical reactor problem, here I have to solve dynamic optimization problem. So first of all, single objective dynamic optimization problem itself is a challenging task. So we want to do that single dynamic optimization, but with multiple objectives. So it is like multi-objective dynamic optimization problem, or multi-objective optimal control problem. And all of them we did simultaneously. And as I mentioned earlier, that here the flow rate or the variable, action variable that I add to the reactor, I have many possible solutions. So what we said that I will optimize not the entire profile, but rather 1, 2, 3, 4, and 5 points of substrate flow rate, or rather the flow rate to the reactor I will optimize. So that effectively I'm saying that this flow rate could be here or here or here, anywhere. So optimization will decide that it should be here, above, or elsewhere. And in between, I'll join them by line. Okay. I know that it is not very easy for you to understand that, but this is just more detail, that how we can solve a dynamic optimization problem. The approach of solving a dynamic optimization problem. You may not be able to appreciate, but you can appreciate that how I add the flow rate of the substrate from outside with respect to time. That problem can be understood with the help of control vector parameterization for solving the dynamic optimization problem. Okay. And this is more mathematics. I won't go into detail. Yeah? And again, very similarly, here also we got yield and productivity, both the objective functions. Yeah. Now here I want to maximize the productivity and yield both. So ideal point for me is lying here. So all those possible operating points which are lying as close as possible to this ideal point are these. Yeah, these are the points. So these are my solutions. Yeah, and the maximum productivity I got was 0.362. Okay, minimum was 0.182, and the corresponding yield are also mentioned here. Okay, and how do we now this is one of the summary, that if I want to, let's say, get point A, which is A, like maximum yield. For maximum yield, I get minimum productivity. Okay, this is the compromise. For that, the substrate that I feed is in this fashion, this red color curve with time. So you have to operate for 30 minutes of time, and you have to add it like this. Very slowly you have to add. But if you want product point B in the reactor, that means maximum productivity, then you add very fast. This is the blue color line. Yeah. So this solution we get by solving dynamic optimization problem, dynamic multi-objective optimization problem. Okay. So again, we get a menu of solutions, and depending on my choice, I can take any of these solutions. Very similarly, I'll not go into this detail. Very similarly, productivity and fed batch operation time. I want to minimize this and I want to maximize this. Yeah. So my ideal point lies somewhere here. So these are the closest points to this point. And these are the solutions. And people, and these are many of solutions. Yeah. So those who are design engineers, they'll be able to appreciate this a lot. Okay. Vehicle design engineers. Okay. And I think I'll not go too much into detail. I have solved a couple of other problems as well. And finally, all the three criterion I have considered, like maximization of yield, minimization of time, batch operation time, and maximization of productivity. Yeah. So somewhere, you know, ideal point would be, I guess, somewhere here, maximum, minimum, yes. Here would be the ideal point. So these are all the possible closest solutions from the ideal point, which we obtain by multi-objective approach. Okay. So I know it could be very heavy. It could be very heavy, but this is what it is. In summary, I would say that you can design, whether it is a reactor design, whether it is a mechanical system design, whether it is a civil structure design, as long as you can identify what are the criteria. Number one, you can also, if you can identify what are the action variables possible. Number two, and if you can identify the constraints, practical constraints, you can solve this problem. And I tell you, huge benefits you get both economically and otherwise, or academically as well. So I don't know whether I have done enough justice to, at least other than chemical engineers, but hopefully there is something you might have got. I think I'll skip. There are more things to show, but I think I'll stop here. I'll be happy to answer any question.
I request all the participants, you can put your question in chat box or raise your hand so that we can unmute your mic. Anyone from the participant?
I usually say in my class that many times we feel that, the question that I have is very rubbish question. I would say that rubbish question is the important question. So if you feel that your question is a rubbish question, the kachra question, actually you should ask that, because that is actually the important question. Okay. So if you have that kind of question, feel free to ask. I'm sure that you may not have understood many of the things that I've said, but that is fine. Even if you have got something and have any question related to that, I'll be very happy to answer. Any effect of RTD in optimization of it? Oh, very good. Yeah, so I understand. Yeah. So in continuous reactors, we are aware, at least chemical engineers are aware, that all the reactors are not ideal. So if I talk about the first reactor, not tubular reactor, yeah, we have assumed that there is perfect mixing across the radial direction, but that may get violated. Yeah? If it gets violated, then you have to get the model which satisfies non-ideality. Yeah. So our optimization results or design results are based on the model that was developed by someone else, some other researcher who had developed with a lot of ideal conditions. So if those idealities are challenged and non-idealities come into picture, then the corresponding model will change. So mathematical model will be slightly different than the current model. But our optimization approach will remain the same. Our optimization idea will still remain the same. Problem formulation will still remain the same. But the final solutions will change. Why? Because the model repeations are changed. Yeah? But the approach of solving multi-objective optimization, the approach of solving design will still remain the same. Thank you. It was a very nice question. Maybe I'll see the chat if there are any more. Yeah. Is there any other question?
Yes, anyone?
Feel free to ask me any question wherein you might have done some optimization. If you might have done, if you might have taught, let's say, reaction engineering, or if you've done, if you operated reactor, or you have done optimization for any mechanical, electrical computer system, and if you want to relate that over here. Yeah, component balance will change. I would say that component balance will not change, but the non-ideality condition, because of the non-ideality, the flow conditions will change. And this non-ideality in the flow has to be combined with these reactor conditions. And then we have to consider simultaneously before we can solve the multi-objective problem. Yeah. So somehow non-ideality conditions we have to incorporate into our modeling of the reactor. Yeah. But as I mentioned earlier, our contribution was not in modeling part. Our contribution was in optimization and design part. But this modeling part has to be done if it is non-ideality, or you want to consider non-ideality and combine with the ideality, and then solve the design problem. Correct. Thank you. So there was another question I had got. Component balance will remain the same, but it has to be augmented along with the non-ideality in the flow. That is how typically it is done for non-ideal reactor design. Yeah. Is there anything else?
Sir, I have one question.
Yeah, please.
Sir, in natural gas, methane is around 70 to 90%, and rest of other hydrocarbon. So my question is, how to remove the hydrocarbon other than methane to increase the yield of hydrogen?
Okay. So yeah, so one option, as you mentioned, that can we purify and remove and filter other components and then send only methane in the reactor? We can possibly do that. But the question is that, is it economical? Why? Because gas separation is a very, very expensive job. It is very expensive operation. So as long as they're not poisonous, we don't mind. I mean, we send methane and other gases along with the methane in the reactor, and we'll get some side products, and we don't mind it. Why? Because compared to separating methane from other gases, this option will be less costlier. Yeah. So it's okay. Even other gases are there along with methane. Some side products will get, but that's okay. But majorly, as you mentioned, that 70 to 90% is methane. So primarily we'll get hydrogen. And even if I take, let's say, propane or butane or ethane, that also reduces to hydrogen as well. So from there also we'll get some hydrogen. So instead of separating, I would say that, not separating is a better option. Why? Because separation costs, and we can save that cost.
Okay, thank you, sir.
Yeah, very good question. Huh? Thanks. Is there any other question?
Anyone else from the participant?
I know they are in hurry for the dinner. And I'm really in between your dinner and now. Dinner and you, yeah. Okay. Okay, then if there is no question, I think we can end the session here, right?
Yes, sir. Sir, I would like to extend my gratitude to Dr. Nitin Padiyar for sparing his valuable time today. Your presentation was very insightful and provided with a lot of valuable information regarding multi-objective process optimization of natural gas, tri-reformant in tabular and spherical bed reactors. I truly feel that this knowledge will help us a lot in the years to come. I thank all the participants for joining this class. We will be meeting tomorrow as per schedule. I request all the participants to make sure that you join the session on time. On the behalf of program coordinator, I announce that today's session is over now. Thank you so much. That's all for today.
Yeah.
Thank
Okay.
you.
Yeah, thank you. I'll leave, right? I'll leave the session right now.
Sir. Yes, sir. Yes.
Okay, thank you.
Dr. Nitin,
Yeah,
there is one interaction session, I think so, for only for 15 to 20 minutes, hardly. So we can take a break here for the
Mhm.
second session, and then after 10 to 15 minutes, we will again join if the participant has certain queries or some interaction. Then we can wait for another 15 minutes, and then we will close the session.
Okay, sure, no
Okay.
problem.
So I think right now, Rajeshwar, after this session lecture second, we can have a break for 10 to 12 minutes, and then we can have an interaction session, hardly for half an hour, 15 minutes. Fine.
Okay, sir.
Uh,
Okay, sir. Okay.
that session will be only up to 8:50, so I'll be traveling, but while traveling, I can address the questions and we can
Yeah,
discuss.
it is just only interaction, and basically our presentation part is over, and only interaction will be seen through if any participant has certain queries. So, sir, I think you can, while traveling, also we can discuss.
Yeah, I can manage, so we can.
Okay, fine. So we can have a break for 10 minutes.
Sure, sure. Huh?
Okay.
Okay.
Hello, sir. Hello. अच्छा actually sir का हाँ हाँ
Yeah. 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 So hi, I'm available. I'm ready to discuss if you have anything. I'll not be able to switch on my video, but yeah, my audio will be on. Let's discuss.
Yes, anyone from the participants to put out your question?
Dr. Nitin, I have one query
Yeah. Please go ahead.
that generally in our chemical engineering, when we are going to do optimization for certain mass balance equation, what we are getting with constraint and some parameter we want to optimize whose order is in the thousand, and another parameter we want to optimize whose value is very, very less. In that
Correct.
case, gradient descent method is generally applied for linear and non-linear optimization. But
Mm-hmm.
many cases, what we found that this gradient descent method do not work, and the converse of the equation will not take place easily. Whatever if we are changing the constraint and different bounds. So, is there any rule that by which we can escape from this gradient descent method and can apply another method of optimization for our engineering based problems?
Yeah. Yeah. So let me give you the perspective. Huh?
Yeah.
What happens that typically this is one of the issues of gradient based methods. Okay, so um, if the problem is linear optimization, then you do not need to use, let's say, gradient based methods. Directly you can use simplex method, and that is
Yeah,
very
simplex is generally used for linear, but for
linear.
non-linear, many times the gradient descent method do not converge easily our
Ah,
base problem. When there is a great difference between the response values, one thing we want to maximize, another we want to minimize, and the delta value is very high in that case.
correct. So for non-linear, no, this is one of the challenges. And compared to this sequential quadratic programming like steepest descent or Newton's method, interior point interior point optimization techniques do better job as compared to this steepest descent and Newton's method and so on. So, for example, like FMINCON, it works on SQP, sequential
Yeah,
quadratic programming,
yeah,
right?
yeah.
And there is a IP opt available, developed by, let's say, Professor Bigler from Carnegie Mellon University. So I have solved, let's say, maybe 5,000 variables problem with the help of IP opt, which is non-linear. So it converges. It converges very nicely. So FMINCON actually doesn't work very efficiently, or Stevenson descent method doesn't work very nicely if the number of variables are more, especially when it is non-linear optimization. I agree. So IPOP, interior point technique,
Maybe
works great.
more better in that case for
Yeah.
non-linear.
Yes.
Yeah.
Agree.
Secondly, can you suggest for the participant that as compared to the different other technique like evolutionary method and annealing technique and particles on optimization,
Yeah.
for our chemical engineering basically problem, which type of
Mm.
technique should we adopt first as compared to all these parallel techniques for non-linear problems?
Yeah. Sure. Sure. So these earlier methods that we talked, no, let's say Newton's method or Steepest descent method. So those methods are gradient-based methods, right? And
Yeah.
what they do, they solve a particular type of problem, which is called single objective non-linear optimization problem. Okay. Now,
Hmm.
one of the primary disadvantage of these methods, these kinds of method, no, this kind of methods is that it converges to a local minimization or local maximization point, right? So I may not get the best of the best points. Yeah, this is one of the limitations. Another is there may be some convergence issues. Why? Because I'm using gradients. Now, sometimes when gradients are zero and the gradient term is in the denominator, it doesn't converge. Yeah. So these are some of the limitations. These limitations are nicely taken care by evolutionary algorithms that
Evolutionary.
yeah, that you just mentioned, no? like particle swarm optimization, then differential evolution, then genetic algorithm, and so on. I would say that we don't have to worry too much about whether I should use particle swarm or differential evolution or genetic algorithm, because one will take a little more time than the other. For us, getting the good solution is more important, right? So generally, if you go for, let's say, differential evolution or genetic algorithm or even particle swarm optimization, they'll do a very good job for solving engineering applications. The advantages of these methods, like evolutionary methods, is that they really give you best of the best solution. Yeah, there is global optimum solution, not with guarantee, but most of the time. Only the problem with that is that it will take a lot of time to get the solution. Okay, so I would say that for chemical engineers and even for other engineers, for solving offline problems, which are generally the design problems, it is always a good idea to solve using
IP,
evolutionary algorithms.
evolution.
But many
And
times when we want to do optimization online, for example, in control, in model predictive control, you have to go with the classical methods like steepest descent or those kind of methods, gradient-based methods. So this is how I would like to summarize, when to use what.
okay, and at the same time, we have to very basically check alarm what type of method can be adaptable for different basic problems. It doesn't mean that we can use only single type of method each and every time.
Yeah,
Yeah,
agree.
yeah. So
So,
I participants can have certain queries they can ask because very nice presentation is already been given by Dr. Nitin Padiyar last 2 hours regarding the design of the reactor as well as optimization for multi objectives. Control optimization is also has been considered very well. So
yeah.
participant, is there any queries? You may raise the hand so that we can unmute it. Yeah.
Yeah. Yeah, I'll be happy to answer any other question as well.
Yes, anyone from the participant to put out your question?
Any query from the participants? I think Rajesh sir, now you can conclude.
Sir, I have one question.
Yeah.
Sir, in tabular reactor, I think iron oxide and chromium oxide bicatalyst is used for the production of hydrogen. So is any catalyst is used in spherical bed reactor? And what about the conditions? Is that same or different?
Yeah, please bear with me. There will be
Hello?
some yeah. So there will be some disturbance because of the noise around me. But I got your questions. Let me address that question.
Mhm.
So your question is that typically this hydrogen production, no, it is catalytic reaction, right?
Yes, sir.
Now because of using one catalyst versus other, the operating conditions will change in optimization solution, and I totally agree. Yeah. So I would yeah. You're able to hear me, right?
Yes, sir. Yes, sir.
Okay. So I would like to answer in this question. So if you have one catalyst versus other, depending on to what catalyst you want to use for effectivity and so on, your kinetic parameters will change. Equilibrium parameters will change. Sorry, equilibrium parameters will not change, but kinetic parameters will change. And accordingly it will affect your rate of reaction, and accordingly it will affect the mass balance results dynamically. So solution that you get for one catalyst, the solution will be different for the other catalyst, for sure. Yeah, but the depending on to what are the kinetic parameters depending on to what catalyst you are using. Okay, but the way how we solve the optimization problem, the way how we do multi-objective problem, the way how we design the reactor will still remain the same.
Yeah, it will reveal
But
the
I
same.
totally agree that the final values will be different. The final temperature, the final feed conditions will be different, and it will depend on to the
Properties of the catalyst and different other interaction parameters.
Hello. Hello, Dr. Nitin sir. Your sound is breaking now. Hello.
Rajeshwar, your problem is very impressive. Query is impressive. Only the what I can, because the sound is breaking. So what I can say that on behalf of Dr. Nitin, who want to say that only the interaction parameter will change the physical properties during the mass balances. However, the methods of the optimization is remain same, and the output of the optimum results may be different because of the physical properties are changed because catalyst to catalyst in the spherical reactor. So I think you have the solution of this query, and
Yes, sir.
now you can conclude to whatever the session has been done by Dr. Nitin Patel in a very excellent manner. So please conclude, and we can end the session accordingly.
you summarized very nicely. Thank you very much.
Rajesh sir, please conclude.
Hello.
Oh, oh, oh.
I would like to extend my gratitude to Dr. Nitin Padiyar for sparing his valuable time today. Your presentation was very insightful and provided with a lot of valuable information regarding multi-objective process optimization of natural gas reformer in tabular and spherical bed reactors. I truly feel that this knowledge will help us a lot in the years to come. I thanks all the participants for joining this session. On the behalf of program coordinator, I announce that today's session is over now. Thank you so much.
Okay. Thanks, Dr. Patel, for giving such a nice presentation, and thank to all the participants too.
Yeah, thank you for inviting me. It was very nice experience. Thank you. Thanks a lot.
Okay. Good night.
Good night.